Join the conversation.
Join the conversation.
You're with Cape Talk.
We've been speaking a lot about interest rate hikes. We've been in such a cycle in South Africa of late. And of course, it's taken its toll amongst us, the middle class. The bonds are costing a lot more. And of course, your short-term insurance and stuff and car finance costing a lot more. But imagine this. Turkey has hiked its main interest rate from 8.5% to 15%. So that's the equivalent of the repo rate. They've hiked it by 6.5%. That is a big blow. And I have no doubt people will be reeling as a consequence out on that side. But it's time for the Naked Scientist. Chair of Science at the University of Cambridge, Dr. Chris Smith, also known as the Naked Scientist, joins us on air once more to answer a variety of science-related questions. Welcome back, Dr. Smith. Always good to have you.
Morning, Clarence. How are you?
I'm great, thank you. The clouds are gathering after a bit of a respite from the rain. So I guess there's some more rain in store for us. But 'tis the season, I guess. Naked Scientist, what are the benefits of cold water swimming? Is a message in.
Well, I'm not sure there are huge numbers of benefits other than what people allege the benefits to be. Some people say it's great for them and they really enjoy it. I'm not one of them. I can't stand cold water. It makes me shiver and shriek and I can't stand getting in it. But the people who are really into this, they go swimming in the sea at Christmas time and things like that, they say it's enlivening. They say it gives them a huge energy boost. It certainly puts your metabolic rate up because, of course, you're stimulating your nervous system very hard with all this cold water, and it puts you into a kind of shock response, which pushes up your heart rate, pushes up your blood pressure a bit, and causes you to burn more calories to restore the lost heat. So some people do find it enlivening, but I'm not sure that there's a really strong evidence base that this is more beneficial than just the exercise alone. Exercise is brilliant, so definitely take the exercise, but don't feel compelled to go into freezing cold water if you're not enjoying it, because at the end of the day, part of taking regular exercise is that is the good for you thing, and you've got to enjoy it to want to do it.
It's a growing fad, just jumping into our cold Atlantic Ocean. Temperatures around 12 degrees at this moment in time, and they're claiming medical benefits. Maybe we should sober up. To the comments there from the Naked Scientist. Here's a WhatsApp voice note in. Let's take a listen, Joe.
Good morning, guys. Good morning, Clarence. If you could explain to us with regards to this whole submersible thing, what is a catastrophic implosion? I know the pressure is hectic, but what pressure, how much pressure is on the vessel per square inch? Just so we can get a better understanding. And would it be instant? Would they not even realize what's actually happened? Yeah, I'm just curious as to what could have happened with this recent disaster.
Yeah, a lot of questions we have, Dr. Smith.
Yeah, this story dominated the headlines across the world, didn't it, all week? The answer to this is that let's think about when we're at the surface. When we're at the surface as a human, walking around, we have the mass of the atmosphere extending about 100 kilometres up to the edge of space above us. And if you add up all that gas that's pressing down on us, you've got about 10 tonnes per square metre of pressure on you. Now, for every 10 metres you go underwater, because water is heavier and much denser than the gas that's in the air, you get 1 atmosphere per 10 metres. The submarine that was lost, or submersible that was lost, was lost down where the Titanic is, which is at the bottom of the Atlantic Ocean, about 400 miles off the coast. And the water depth there is about 4 kilometres, so 4,000 metres. So if you divide that by 10, that tells you that the pressure on that submersible, and if you were outside the submersible, the pressure that would be on you is 400 times the pressure at the surface. Now, the average person at the surface is feeling a pressure. I said it's 1 atmosphere, but that's about 10 tonnes per square metre. So if you're 400 times greater than that, you've got 400 times that pressure per square metre on you as a submarine. So that's a stupendous amount of pressure. It's enormous numbers of African elephants standing on every square metre of the subsurface, pressing in. And the reason that the sub had, or any kind of submersible, deep submersible, uses a round or semi-spherical structure is if you have curves, you have no angles where force can concentrate and materials are less likely to fail. So by making things round, and this is the same reason on aircraft we make the windows round, on spacecraft we make the windows round, and on ships we have round portholes, because then you have no point for force to concentrate. So it's easier to dissipate evenly the force and pressure in all directions to keep it safe. The vessel's hull was part metal, but was a carbon fibre, at least 6 inches thick shell, which again is a round shape to help distribute the load and the pressure evenly in all directions. But all it takes under those sorts of enormous pressures is one tiny breach, one material structural failure or weakness, and you will get a progressive failure point where, as you damage the material a bit more and it deforms, it forces a concentration of the force at that failure point. So it then goes into a sort of positive feedback loop. It becomes weaker, which deforms it more, which concentrates more force through that point, which means it becomes weaker, which concentrates more force. And it goes into a positive feedback loop that will cause an almost instantaneous catastrophic implosion. So you've got all these thousands of tons of pressure pushing in on you, and it will go from normal size to tiny in a very short space of time. People say sort of milliseconds. The one saving grace is that the people inside would not have known what was happening because it would have just happened in an instant.
Then we have another related question. Dr. Chris, if you were ever given the chance to go into a submersible, would you Samantha out in table view with that question?
Well, I asked Frank Owen this. I interviewed him yesterday. He is a retired Navy commander in Australia and also was a director of the Submarine Escape and Rescue Service there. And I said to him at the end of our conversation, with your lifetime experience, would you go to sea in that craft? And he said, knowing what I know now about the craft in question, I wouldn't go to sea in that craft, and certainly not down to 4 kilometres beneath the surface, because they're just, it's A, incredibly dangerous as an environment anyway, and B, you need to have the best equipment in order to survive down there, and anything could happen. And indeed, it did happen on this occasion. It's very, very hard when you're working at the limits of what technology can take like that to be completely safe and to have no risk. And some people are comfortable with a bit of risk, but many people say, well, I'm not comfortable with that risk. So I think I would be with him. I think at the moment, given the track record, and the fact that it's harder to go to the bottom of the ocean than it is to get into space, to be perfectly honest with you, I think I'll stay here on the surface.
Yeah, I think I'll join you on that one. The stresses that come to bear, they're not necessarily visible, so you won't be able to see the chink in the armour as well, I guess.
No, and all it takes is one tiny breach, one tiny crack or scratch, and the material can begin to fail. Now, the way that you safeguard against this is you hugely over-engineer these structures. You know roughly what they should be able to take, and on a good day, what they will take, but you say, I'm going to over-engineer with a huge safety margin this so that it has a lot more headroom than that, because that way there can be some distortion, there can be some damage, there can be some breaks or breaches, and it is not going to fail. But it is impossible to de-risk it completely, and things do and can go wrong, as we've sadly seen. And this means that even with the best will in the world, you can never prevent all accidents and all disasters. Even if you're sending rockets into space and you've got teams of thousands of people and you have budgets in the billions, things can and do go wrong, even with the best planning. And one has to accept that this happens from time to time. And to a certain extent, it's thanks to pioneers who will say, well, I'll take that risk, I'll go for it, that we are where we are. Because if you think about it, hundreds of years ago, no one had crossed an ocean. And it took some very brave souls indeed to say, well, okay, I'll get in a boat and I'll sail off over there where it looks like I'll fall off the edge of the world, because when a boat goes over there and I watch it disappear into the distance, things seem to disappear. So I'll keep going into the unknown. I may not come back. I'll take that risk. And so there are some brave people who will do this, but I'm not sure I'm brave enough to join them.
Dr. Chris, what are the relative sizes of a proton, a neutron, an electron, and how big is the hydrogen atom relative to the proton?
Well, electrons are absolutely tiny. They weigh a fraction of what a proton and a neutron does. So when we're calculating the masses of atoms, we regard the electron mass as essentially negligible when we're actually weighing out the atoms. Protons and neutrons are roughly the same size, and they're roughly the same weight, and we assign a relative weight of 1 to them. So in a hydrogen atom, there is 1 proton and 1 electron, so we say it weighs 1. Its mass is 1. And we calculate the mass of all the other elements relative to hydrogen. So we have a relative atomic mass. So the next element in the periodic table is helium. Helium has got 2 protons and 2 neutrons. So therefore, it's actually got a mass of 4, but its atomic number is 2 because it's got 2 protons. So it's 4 times the mass of hydrogen. The next one is lithium, and so on. So relative to the electron, we disregard that mass because the protons and neutrons are so big and so heavy. Most of the space in an atom is empty space because the core, the nucleus, is very tiny, very compact, and highly charged. That's where the protons are. And the electron or electrons exist in a cloud. You can think of it as like a cloud all around the atom. And the electrons spend different amounts of time in different places around the atom, but they're everywhere and nowhere all at once. And this is the confusing thing. This is where Schrodinger's cat comes in. You have to force it to make a decision about where it is, but until you make a decision about where it is, it's everywhere. So the electrons are in a cloud around the atom, but because they're everywhere and nowhere all at once, most of that atom is empty space. And this was what Ernest Rutherford discovered in Cambridge about 100 years ago when they did the famous experiment that completely rewrote our understanding of the structure of atoms. They were firing alpha particles, which are the nuclei of helium atoms, at a very thin sheet of gold. They chose gold because you can hammer gold to be literally individual numbers of atoms thick. And they were surprised when they fired these nuclei at the gold to see that occasionally some would come pinging back like a ricochet, a bullet hitting a wall, towards where they sent the particles from. Now, this was completely at odds with our understanding of the structure of atoms, which until then people had thought that an atom was like a ball and it was a mixture of plus and minus charges all mixed up. And the only way you could reconcile a tiny nucleus hitting something and ricocheting back to get the force that would do that is if all the positive in an atom was concentrated in one tiny place and surrounded by a sea of negativity, electrons. So that rewrote our understanding of the atom, and we then went into the almost solar system type model of atoms, where we had a tiny nucleus with all the charge, the protons and the neutrons in the middle, and the electrons in a cloud, more diffuse around the outside, with most of the atom being empty space.
Let's go to a voice note. Joe's got a voice note for us. Dr. Smith, of course, the Naked Scientist, with us.
Good morning, Clarence. Can you please ask Dr. Chris, why do all newborn babies have straight hair? And then later in life, well, either their hair stays straight or it becomes curly, like in Chris.
Hi, George. Well, when babies are born, they prioritise what they grow, what they develop, and what they prepare so that they're in the best shape possible. And I don't mean physical shape. I mean as in they are as best prepared as they can be to survive as soon as they're born, because they're literally cutting their life support machine off as soon as they're born. The umbilical cord that connects baby to mum via the placenta is dealing with all the baby's waste and bringing in all the nutrients it needs. As soon as that is cut and the baby is outside, it has to be responsible for bringing in its own raw materials, oxygen so it can survive and breathe, and food. It's got to be able to swallow and absorb that. And it's got to be able to alert mum and dad when it wants some help by crying. And it's got to wake up and sleep and move a bit at the right time. So it prioritises doing all those things, and it deprioritises things that are less essential for life. And other things which are less essential for life include stuff like hair. You don't need that inside. It may also clog up the works when you're trying to come out, and shed hair could get into places you don't want it to. So you tend to not waste protein, which is what hair is. You don't waste essential proteins on growing loads of hair when you're inside. You minimise that until later on in pregnancy, so you grow your hair later when you've got a better supply of protein from your diet. So really, hair is not a priority for survival, so therefore it's relatively immature. The follicles are relatively immature. They're going to produce the hair, so it isn't in the adult characteristic structure or colour in a baby as it's coming out, and that develops a bit later on.
I'm going to read this question the way it's written. There are numerous reports of orcas, killer whales, attacking luxury yachts in the Mediterranean Sea. Experts say they are teaching each other to attack the yachts. Can this behavior be unlearned? Quote, unquote, that one from Andries.
This is true, and a number of people have reported that their boats have been struck. And the animals are allegedly teaching each other to do this. These are social species. They are very intelligent, they have big brains, they're mammalian species, and they live in communities. as social creatures. And just as we teach each other, or we watch each other and we watch and learn, these other animals do the same thing. Fish, which are not mammals, do the same thing. They're social species and they can learn from each other. Birds do exactly the same thing. So it's not altogether surprising that this group of animals would watch and learn, but why they've decided to target these boats, that's not altogether clear. Orcas have an interesting relationship with humans. In the past, there have been stories of orcas working collaboratively with humans. There were stories in the whaling days in Australia where there were orcas that used to help the fishermen who would go out to catch the whalers, to catch whales. They would actually assist the whalers in finding whales and harpooning them. Under these circumstances, the orcas seem to have turned on these boats. I suspect it's because one of them had a brush with a boat in the past which hurt it, or it regarded as a threat because of the boat perhaps colliding, and as a result it's decided to exact revenge. This is a threat, we need to get rid of it, and it has enlisted its other colleagues to come and help. And perhaps if a dominant sort of top of the chain hierarchy animal has decided to do this, the others will, out of loyalty to that animal, follow suit. So that could be what's going on. But I know people are studying this and they're looking to see what's doing it, who's doing it, and perhaps why they're doing it. So as more details emerge, I'll pass them on.
Dr. Chris, I have a glass hob in my kitchen. When I'm cooking, the heating element glows red and the heat moves through the glass to the saucepan. I can put my finger onto the glass next to the saucepan and it's barely warm. So how is it that the heat is readily transferred vertically through the glass but not laterally across the glass? Barry in Cape Town with that question.
The most likely explanation for this is that the heating element is glowing nice and hot, and it's therefore, because it's glowing in the infrared as well as visibly red, and so it's producing radiation, which is nice red end of the spectrum, and this is being absorbed by objects which are close to it, within line of sight, and that means the saucepan above it. But the infrared is not reaching the glass farther out across the hob surface. It would have to use conduction through the glass to do that. And if you have an overlying ceramic, which is a less good conductor, then it may allow the heat to pass, or the infrared radiation to pass through, because it's transparent to infrared, so it'll pass through, but it won't conduct the infrared very far laterally around the surface of the hob. And that makes sense, because you don't want to conduct the heat away from where you're heating the pan, because then less heat is going into the pan than heating up the surface of your hob. So I think that's the most likely explanation here. You have a surface which is transparent to heat or infrared waves, so they can pass from the heating element into the thing which is soaking up those infrared waves, and the glass or ceramic surface is good at doing that. It lets it through, doesn't absorb it very much, and because it doesn't absorb it very much, it doesn't conduct it very much to other areas around abouts on the top of the hob.
On the question of orcas, and we've seen a couple of them in our seas around Cape Town, are there any records of orcas killing humans? A question in.
Almost certainly. I'm not aware of an exact case study I can cite, but I would say it's absolutely the case that there will have been human fatalities through interactions with orcas, including in some wildlife parks. I think there have been instances where that has happened.
And we're going to have to rest it there. We're out of time. It is nearly 10 o'clock. We're going to news. A big thank you to the Naked Scientist, Dr. Chris Smith. He joins us every Friday at 9:30. And then, of course, you can liberate that question that keeps you awake at night. Some more of him next week, Friday at 9:30.